So thank you very much for your kind introduction and good morning, everyone. I'm Norihara from Riken, Japan, and today I'm very happy to present my talk, especially after my supervisor when I was an exchange student in instrumentation physics laboratory in 1998, Professor Saroma, and also after my senior in Osaka University, who is Fujita-san. Professor Fujita in Osaka University, who was also an exchange student in instrumentation physics laboratory in 1997. And I'm very much honored to give my talk after them, entitled by Tip Enhanced Raman and Terahertz Nanospectroscopy. And first of all, here is the acknowledgement for the work. The work I'm going to introduce, especially in ambient system, has been done with the members in photon team members in Riken. And also the works done in electrochemical environment and ultra-high vacuum low temperature environment have been done with the members in surface and interference science laboratory in Riken. And I'm also collaborating with many professors in P and MSEP, as well as Tani Sensei and Kuya-san in Fukuoka University. So thank you very much for your help for the research works. Anyway, the topic I'm going to talk about is the tip-enhanced Raman spectroscopy, TERS. This is a combination between scanning probe microscope and optics, particularly near-field spectroscopy, so that we can achieve both high spatial resolution and high chemical sensitivity. And very briefly about tip enhancement effect. And so when a nano-sized metallic tip is irradiated by the light field, the collective oscillation of the electron is induced inside the metal. As a result, the enhanced electric field is generated and localized at the tip apex. So when you employ this enhanced electric field as a nanoscale light source for several spectroscopy techniques, such as Raman spectroscopy, you can acquire local Raman spectrum underneath the tip. And also when you scan the tip over the sample, you can acquire local Raman imaging beyond the diffraction limit of the light. And what can be seen by this technique, for example, is here is the carbon nanotubes dispersed on the cover slip. So you can see lots of carbon nanotubes by AFM topography here. This is the AFM topography. But when you employ conventional confocal Raman microscope using a lens, because of the diffraction limited focus spot size like this, you cannot spatially resolve each carbon nanotube. So in the case of tip-enhanced Raman spectroscopy, what you need to do is to bring the tip onto the diffraction limited focus spot and generalize the nanoscale light source like here and scan over the sample so that you can clearly visualize each carbon nanotube spatially like here. In this case, we achieve the spatial resolution up to 20 nanometer. And after that, we have developed lots of optimization in ambient tip-enhanced Raman spectroscopy. For example, the improvement of the humidity and temperature control using the environmental control chamber. And also we developed the reproducible tip making system using 3 electrode etching system. And also we can precisely now tune the tip plasmon and the characterization of the tip plasmon by some spectroscopic techniques. So you can control very precisely the tip plasmon resonance as relative to the wavelengths you are using. And recently we have compiled and summarized these efforts in the progress review published in Japanese Journal of Applied Physics, written by Bani from NIPP4. Then after this effort, what I want to emphasize in this paper is now we can achieve the spatial resolution of up to 1 nanometer by Raman spectroscopy in ambient environment. So aside from actually the high spatial resolution by tip-enhanced Raman spectroscopy in ambient, we have found very unique physics in such a nanospectroscopy. That is the new selection rule in Raman spectroscopy. For example, we observed the activation of forbidden phonon mode from graphene. So here, the sample is defect-free graphene. And as you may know, the D-band represents the defect mode of graphene. So it means without the defect, this mode is forbidden phonon mode. However, we observed, for example, here, we observed very strong D-band in our tip and Raman spectrum, although our sample is defect-free. And based on the fruitful discussion with Professor Riichiro Saito in Tohoku University, who is a very famous and active professor in the field of theory on graphene carbon-related materials. Recently, Saito Sensei published a unique paper, theoretical paper, entitled by Non-Vertical Optical Transition in Near-Field Enhanced Spectroscopy of Graphene. But today I have not much time to introduce the detail of this work, but the point is because of the highly confined electric field, you can achieve very high wave number from the enhanced electric field, which compensates the momentum mismatch in the electron-hole pair recombination or the Raman process, so that the forbidden D band is now activated by our tip-enhanced Raman spectroscopy with 1 nanometer spatial resolution without the defect. And aside from the work in ambient environment, we extended our work, tip-enhanced Raman spectroscopy, to ultra-high vacuum low temperature. And especially this work is for the single molecule resolution and single molecule sensitivity. And in fact, our colleague, Dr. Hakurubia Raf, as you may know, will give a talk about this topic the day after tomorrow. So please find the detail the day after tomorrow. So today I will not talk about the detail. So please expect his talk the day after tomorrow. And in addition to ambient and ultra-high low temperature, we are also extending our work, tip-enhanced Raman spectroscopy, to liquid environment, especially here towards in situ electrochemical environment. So it's inside the liquid. So working with my colleague, Dr. Yokota, we have designed a unique electrochemical cell like here, employing 4 electrodes, including 2 working electrodes. The tip and sample is also works as a working electrode in the electrochemical system, so that you can precisely control the potential of tip and the substrate relative to the reference electrode here. And what we have done is to introduce the laser light onto the STM sample junction via this window material. You can characterize the electrochemical reaction in situ by tip-enhanced Raman spectroscopy. And today, again, there is not much time to explain the detail of this work, so you can find the detail in our recent papers published in JBCC, Journal of Physical Chemistry C. But the essence is to use the paraffin wax-coated gold tip. So in order to avoid the Faraday current from the taper of the tip, we coated the gold tip by paraffin to suppress the Faraday current aside from the tip apex. So by using this system, indeed, we can carry out the conventional electrochemistry such as cyclic voltammetry, and also the potential-dependent tip-enhanced Raman characterization during the electrochemical reaction is now possible. And of course, this work can be used for the biological samples in liquid environment. And in the rest of the time today, I would like to introduce our challenge towards nanoscale terahertz spectroscopy today. And one of the projects we are working on this SPM nanoscale terahertz spectroscopy is nanoscale laser terahertz emission microscope, nano L10. So based on the design we're doing here, we introduced the near-infrared laser light onto the SPM junction and focused by this parabolic mirror onto the SPM and substrate junction. And the emitted terahertz light is collected by this parabolic mirror and detected by this photoconductive antenna. And we also developed the home-built non-contact mode AFM for this study. And another topic working on this nanoscale terahertz spectroscopy is so-called nanoscale terahertz time domain spectroscopy. So in this case, instead of the simple mirror here, we employed another photoconductive antenna developed by Fukuoka University, Tani Sensei. So the near-infrared light excites the photoconductive antenna and terahertz light is generated and focused by this parabolic mirror onto the SPM substrate junction. And the modulated terahertz signal is collected by, again, this parabolic mirror and detected by this photoconductive antenna. And in fact, what we want to do is to combine these two systems. This is a kind of hybrid system of nano-LTEM and nano-terahertz time domain spectroscopy. That is called so-called nanoscale optical pump terahertz probe microscope. So briefly about this system. So the LTEM bus, near infrared laser pulse, introduced onto the SPM substrate junction to excite the photocarriers. And after a certain delay, control delay, the terahertz pulse is introduced onto the same position, SPM substrate junction, to detect the carrier dynamics from the local volume underneath the tip. So by using this system, we are expecting to characterize the ultra-fast carrier dynamics in the nanoscale in the future. And actually, this work is partially motivated by the recent collaboration with NIP professors and also Fukuoka University professor Tani Sensei. And this is about the intense terahertz emission from the interface between low temperature grown gallium arsenide and N-type gallium arsenide. So in order to understand the physics behind the enhancement of this intense terahertz emission from the interface, the MIMI, Dr. Bargos, characterized its interface by cleaving the substrate like here in situ inside of the STM chamber and characterized the interface by using STM and scanning tunneling spectroscopy. And she compared with this atomically resolved observation with the far field terahertz microscope. But unfortunately, in fact, the terahertz microscope is the far field technique and diffraction limited, especially the terahertz wavelength is quite long. That's why this is kind of macroscopic characterization, although the STM studies has atomic spatial resolution. So in the future, what we are expecting is to employ nanoscale LTEM to characterize the terahertz emission property from the interface in the nanoscale, which can be comparable with compared with the atomically resolved STM characterization. Anyway, owing to this work, MIMI published the paper in Journal of Applied Physics, collaborating with between DCAN and NIP. And owing to this successful paper, thanks to everyone, MIMI became finally Dr. Bargos. So thank you very everyone for your kind help for our study. And actually, the members in DCAN as well as the members in NIP are mostly experimentalists. That's why for this kind of study, we need a very strong support from the theoretical researchers. And that is now provided by Professor Eskando in Fukuoka University. And she characterized and calculated lots of physics found in gallium arsenide materials, such as the arsenic andesite defect in gallium arsenide. Then now we are comparing our experimental observation by STM and STS and compared with the theoretical calculation done by Kuria-san and preparing one more paper, which is also the collaboration between NIP and DCAN plus Fukuoka University. Anyway, based on this experimental observation, as a summary, what we are expecting by using nanoscale OPTP is, at first, by using nanoscale LTEM, we will try to characterize the local terahertz emission from the local volume from around the interface, also around the defect found in the STM image. Also, by using nanoscale terahertz time domain spectroscopy, we are expecting to characterize the local carrier density by this technique. And finally, by using the nanoscale OPTP, we derive fast carrier dynamics around the arsenic andesite or other defects in the future. And we expect this technique is actually applicable not only low temperature grown arsenide materials, but also other semiconductors. That's why I'm very much expecting to further collaboration with. So I think so. Thank you very much for your kind attention.
Good morning. I am Carlo from the University of the Philippines, Diliman, and on behalf of my co-authors, I would like to present our work entitled Room Temperature Optical Emission Properties of Hydrothermal Grown Zinc Oxide Nanostructures. This work is part of a joint research project between the National Institute of Physics and Institute of Laser Engineering, and it is funded by ILE's Collaborative Research Program, Osaka University's International Joint Research Program, and the DOST JSPS Joint Research Program. Our work primarily reports on the room temperature optical emissions of hydrothermal grown zinc oxide nanostructures. We are motivated by the demand of innovative optical technologies, particularly for scintillator material development in the UV region. We want to exploit zinc oxide, a 2,6 semiconductor material with a wide and direct bandgap, has excellent scintillation properties, and is available in a variety of morphologies and nanostructures. However, at the nanoscale regime, the nanostructure morphology and dimensions heavily influence the optoelectronic properties of the fabricated devices. For example, as those observed in detector arrays and LEDs, photons emitted by some nanostructures can trigger or excite neighboring structures, leading to unwanted device properties. In this regard, we want to investigate the optical emissions of hydrothermal grown zinc oxide nanostructures fabricated using different zinc acetate dihydrate or zinc acetate concentrations. Compared to earlier investigations, this work determines the nanostructure's UV emission properties in relation to their preparation, morphology, and dimensions. At NIP, the zinc oxide nanostructure samples were fabricated on seeded silicon substrates by hydrothermal growth method. The substrates were first degreased through ultrasonication and were deposited with 100 nanometer zinc oxide seed layers by spray pyrolysis technique. For nanostructure growth, the aqueous solutions of both hexamine and zinc acetate were initially prepared, wherein a fixed 25 millimolar concentration of hexamine was mixed with 25 to 150 millimolar concentrations of zinc acetate. The seeded substrates were then submerged into these solutions and heated at 85 degrees Celsius for 180 minutes. Now this slide shows the SEM images of the hydrothermal grown zinc oxide nanostructures. All of these exhibit well-defined hexagonal facets or cross-sections. As the zinc acetate concentration increases, the nanostructures become larger, with some sharing common sides or boundaries, or even coalesce to form larger structures. For the comparison of the nanostructure dimensions, we use the side lengths instead of the diameters, considering the partially exposed nanostructures of some samples. As we can see here, a higher zinc acetate concentration results in larger zinc oxide nanostructures. We then performed photoluminescence spectroscopy on the hydrothermal grown zinc oxide nanostructures at ILE. The samples were excited by a 290 nanometer titanium sapphire laser system, and the sample emissions were collected through reflection geometry using a handheld spectrometer to measure their emission spectra, or a spectrograph coupled to a streak camera to measure their emission lifetimes. This slide shows the emission spectra of the hydrothermal grown zinc oxide nanostructures, and all the nanostructures exhibit intense UV emissions which correspond to the near band edge emission of zinc oxide. No visible emissions which can be attributed to the defects are observed. Examining the UV emissions, we can see that for concentrations below 100 millimolar, the emission spectra have single distinct peaks between 381 to 386 nanometers. On the other hand, for concentrations above 100 millimolars, we observe more intense UV emissions with a shoulder at longer wavelengths located at around 391 nanometers. Moreover, this slide shows the UV emission lifetime of the hydrothermal grown zinc oxide nanostructures. All the nanostructures exhibit picosecond UV emission lifetimes, and as the zinc acetate concentration increases, the average emission lifetime increases from 54 to 90 picoseconds. These picosecond lifetimes can be largely attributed to the effective non-radiative recombination with the activation of non-radiative centers at room temperature. With increasing zinc acetate concentration, the zinc oxide nanostructures not only become larger, but also exhibit redshifted UV emission peaks and longer UV emission lifetimes. Since the optical emission detection was done over an ensemble of zinc oxide nanostructures, We attribute these optical properties to the multiple excitation or absorption and emission processes due to the large absorption coefficient of zinc oxide near its near band edge emission. This phenomenon can be illustrated by the following diagrams. Nanostructures have the same refractive index and share common size or boundaries. Under laser excitation, one nanostructure's emission can excite and be readily absorbed by adjacent nanostructures. Additional steps of excitation or absorption and emissions can lead to artificial increase of the emission intensities as well as prolonged emission lifetimes. More importantly, for our zinc oxide nanostructures, this phenomenon can be reduced by using lower zinc acetate concentrations during hydrothermal growth. As shown in the figure, zinc acetate concentrations below 100 millimolar results in zinc oxide nanostructures which exhibit distinct 381 to 386 nanometer emissions and less than 90 picosecond lifetimes, both of which are important for UV scintillator applications. In summary, these zinc oxide nanostructures were successfully fabricated on seeded silicon substrates using different zinc acetate concentrations. Increasing the zinc acetate concentration results in larger and coalescent zinc oxide nanostructures with redshifted UV emission peaks and longer emission lifetimes. These room temperature optical properties are attributed to multiple excitation or absorption and emission processes among the nanostructures. From our observations and for scintillator applications, these processes between the nanostructures can be reduced by using lower zinc acetate concentrations during hydrothermal growth. That ends my presentation, and thank you very much for your attention.
All right. Hello, everyone. I am Romil Emperado, and in behalf of my co-authors, Mr. Mel Sosa, Dr. Lian Dasalias, and Dr. Wilson Garcia, I'll be presenting our paper entitled Thickness Calculations of Thin Films Prepared by Pulse Laser Deposition on Revolved and Rotated Substrates. So as an overview, we want to model the thickness profiles of PLD films on rotated and revolved substrates. So these are off-axis substrates, and we have shown that the profile calculations are consistent with the strongly forward expansion of plasma plumes. Now, how do we model the expansion of plasma plume towards the substrate? Now, we can treat the plasma plume, the laser-produced plasma, as an expanding gas. So this is from a 1996 model wherein the solution for the density and velocity is given by these equations, where capital Xi, capital X, capital Y, and capital Z is the plume front position, and N naught is the total number of particles in the plasma. Now, the product of the density and the velocity gives us information on the material flux anywhere in space and time. Now, modeling the position, we can consider the material flux through a substrate plane for the film thickness. Okay. Now, integrating the flux over time, we can have an estimate of the amount of material that is deposited on the substrate. Okay. Now, the solution by Anthony and his group for the typical geometry given below is this equation, where d naught is equal to n naught times kx ky over 4 pi, where kx and ky are the ratios of the velocities of the plume front expansion. Now, as early as 1995, there are several groups that have been exploring other deposition geometries to minimize the deposition of particulates that are normally have a trajectory along the center of the plasma plume. Now, these off-axis substrates have thickness profiles that are significantly different from the typical center peak thickness profiles in the conventional PLD geometry. And to the best of the author's knowledge, modeling the thickness profiles for tilted and off-axis substrates is not yet explored. Now, what we want to do is to modify the existing model. We want to use coordinate transformations to model film profiles for rotated and revolved substrates. And we want to compare the profiles against the known PLD plume characteristics. And we want to calculate for the mean thickness and roughness for the thickness profiles. Now, for the revolved substrate, this is the equation that we have derived upon upon coordinate transformation. So upon coordinate rotation, the substrate effectively revolves about the target center. And this is the equation that we have derived for that, for the thickness profile. On the other hand, for the rotated substrate, okay, so upon this coordinate transformation, we also translate it back to its initial position, which effectively allows a substrate that rotates in front of the plasma plume. And this is the equation for the thickness profile as a function of rotation angle theta. Now, in order to quantify the thickness profiles, we, as a function of angle, we define the mean thickness as follows. It's just an integral of the thickness profile across the surface of the substrate divided by the area of the substrate. So this is the mean integral for that. Now, the normalized roughness, on the other hand, okay, just describes the deviation of each individual point along the surface of the substrate, its deviation from the mean thickness. And we normalize this mean roughness with respect to the mean thickness in order to isolate the effect of decreasing thickness as you move away from the center of the plasma plume. Now, these are the results. So these color maps illustrate how the thickness profiles rapidly changes as the angle increases. As you can see, the peak rapidly shifts at narrow angles. So this is at 5 degrees. The center of the thickness profile is already near the edge of the substrate. And as you increase further the angle, the thickness profile, the values of the thickness profile decreases up to 2 orders of magnitude slower. Okay, so at wider angles, the thickness value significantly decreases, as you can also see in this line scans for the thickness profiles. On the other hand, for the rotated substrate, the thickness peak shifts towards the portion of the substrate that is near the target. As you can see, as you rotate the substrate, a portion of the substrate is nearer to the plasma plume. So therefore, the thickness profile here has a maximum that is higher than the previous angle configurations. Also, the shape of the profile changes more gradually as the angle increases for the rotated geometry. Now, looking at the mean thickness, as you can see in this figure, for the revolved substrate, the mean thickness decreases rapidly as the angle increases. Okay. And on the other hand, for the rotated substrate, the values for the mean thickness changes by a very small amount, although it is increasing because a portion of the substrate, again, is near the plasma plume than the other portion of the substrate. Okay. So the values are higher than 1. Now, for the mean roughness, as you can see in this figure, the mean roughness for the revolved geometry is highest at an angle where the thickness profile is more steep, which in that case is at around 10 degrees. On the other hand, there is minimal change in profile shape for the rotated geometry. And as you can see, the mean roughness changes by a very small amount as compared to the revolved substrate. In conclusion, the trends in thickness profiles for both revolved and rotated geometry are consistent with a highly forward plasma plume. And the mean thickness and roughness values describes well the profile behavior as a function of angle. So that's it for our presentation. Thank you so much for your attention.
Good morning, everyone. My name is Marvin Binalayog, and in behalf of my co-authors, we would like to present our study about the spectroscopic investigations of polymer composites grown via wet chemical method. Zinc oxide is a wide bandgap semiconductor with approximately 3.4 eV. It has a UV luminescence that is stable at room temperature and a short wavelength light emitting applications such as UV phosphors, LEDs, and lasers. Having a large surface area, ZNO micro to nanostructures have a generally large amount of surface defects, and this has a significant effect on its photoluminescence property, unlike in the case of bulk crystals. Surface defects can subsequently leading to non-radiative carrier relaxation or visible emission due to defect-related electronic transition. And furthermore, ZNO micro-to-nanostructures have many chemisorption sites where environmental molecule species can be absorbed, and this may lead to material or device degradation. By coating or capping surface with ZNO, surfactant, or another material or compound, the surface defects can be passivated and the ZNO surface can be prevented from interacting with uh, unwanted molecular species from the environment, and as a result, the photoluminescence can be improved. In this study, we passivated the surface defects by coating ZNO with polymer, and we will call our samples as ZNO polymer composites. We use the term composites here since it is generally composed of two different materials, metal oxide ZNO and a polymer. We also investigated the effect of different polymers on the photoluminescence properties. We used three different polymers. One is non-ionic PVP or polyvinyl pyrrolidine, a cationic PAH or polyallylamine hydrochloride, and a high charge density PDDA or polydiallyl dimethyl ammonium chloride. Polymers can interact with ZNO surface through functional group. For PVP, the carbonyl group can interact with ZNO on, with hydrogen rather on the surface by hydrogen bonding or zinc surface by a coordinate covalent bonding. On the other hand, the PAH or PDDA are polyelectrolyte and they will dissociate in an aqueous medium making them charged. The ZNO polymer composites were synthesized using a combination of two different wet chemical method, a hydrothermal method, and a deep coating technique. First, the zinc microrods were synthesized using a zinc acetate dihydride and hexamine with 8 millimolar concentration were prepared and mixed to produce growth solution. Then the silicon substrate were submerged on a growth solution and heated for 90 degrees Celsius for 2 hours. And afterwards, the silicon substrate were removed from the growth solution and washed with ionized water and air dried. Then, the ZNO microrods were coated with polymer solution using deep coating technique. So, three different polymers again we used, PVP, PAH, and PDDA with 0.1 millimolar concentration. Then the as-grown ZNO on a silicon substrate were submerged on a polymer solution and heated for 50 degrees Celsius for 1 hour. Then afterwards, the samples were harvested and air dried. The diffraction peaks of all samples, the ZNO and the ZNO polymer composites, are indexed with the hexagonal Wurtzitz crystal structure of ZNO. And also, we calculated the ZNO polymer composites that have a similar lattice parameters to the reference as grown ZNO. And the calculated lattice parameter A is approximately equal to 3.252 angstrom, and lattice parameter C is approximately equal to 5.198 angstrom. And all samples are polycrystalline without any detectable impurity. For Raman spectra, the Raman Ponon modes are also indexed with the hexagonal Wurtzitz crystal structure of ZNO with a similar characteristic E2 high Raman peaks. And in terms of structural properties, the ZNO polymer composites are the same with the pure ZNO microrods. And for the PL, ZNO and ZNO polymer composites have a visible UV emission around 389 nanometer that corresponds with the NBE or near band edge emission of ZNO. For the case of pure ZNO, it has a broad visible emission around 549 nanometer that is attributed to the oxygen vacancies. And when this pure ZNO is capped or coated with PVP, the broad visible emission shifted from 549 nanometer to 591 nanometer as a consequence of capping the pure ZNO with PVP. And it also attributed with the interaction of carbonyl group on the ZNO surface. On the other hand, for the case of PDDA and PAH, the visible emission is completely quenched, and it can be due to the absorption of PAH and PDDA on the zinc surface, ZNO surface, since ZNO surface has a negatively charged in an aqueous solution. And one of our literature proposed that this adsorbed polyelectrolyte on a ZNO surface can interact with surface defect, reducing the surface screening and trapping of carriers. And for the summary in conclusion, the ZNO polymer composites were fabricated by coating ZNO microrods with different polymers. The effect of non-ionic PVP and cationic PAH and PDDA polymers on the photoluminescence properties was investigated. The non-ionic polymer, PVP, reduced the visible emission, whereas the cationic polymers, PAH and PDDA, suppressed it, which could be due to the attributed to the difference in their absorption mechanism. And the optical properties of ZNO can also be modified by polymer coating. And for an outlook, a computational investigation of the polymer adsorption on the ZNO surface or interaction with the surface defects. And this work was supported by Osaka University Institute of Laser Engineering through the Collaborative Research Grant, Osaka University through the International Joint Research Promotion Program, and Department of Science and Technology, DOST, and Japan Society for the Promotion, JSPS, through the DOST-JSPS Joint Research Program. And that's all. Thank you.
A pleasant day to everyone. Our study is the evaluation of the neutron spectra in a medical accelerator facility using a modified Bohner sphere spectrometer. In 2018, Philippines recorded about 140,000 new cancer cases, and 50% of these cases received radiation therapy in the management of their disease. Advances in the technology in radiotherapy resulted in radiation treatments with higher energy and higher radiation doses. Higher energy photons with energies above 10 MV provide advantages over the low energy photons in terms of deeper penetration for greater depth dose and reduced skin dose, lesser scattering, and more homogeneous distribution of the dose. However, during high energy radiotherapy treatments, unwanted neutrons are produced as byproducts in the LINAC head through photonuclear reactions between the photons and the high Z materials when the photon energy exceeds the neutron binding energy of these materials. The LINAC head components are constructed mainly of lead and tungsten, which have a threshold energy of roughly about 8 MeV. Neutron production has implications both in the design of the facility and on patient protection. Neutrons can activate the materials inside the treatment room, and exposure of patients to unwanted neutrons may induce higher incidence of secondary malignancies. Typical neutron spectra inside the LINAC room consists of three regions: a thermal peak around 0.025 electron volt, an intermediate component, and a fast peak around 1 MeV. The neutron field varies from one facility to another, and the neutron yield depends on many factors such as the accelerator design, operating energy of the machine, and the design of the facility. The neutron dose is strongly energy dependent, and the neutron fields include a wide range of neutron energies. Several instruments for neutron measurements are available, such as a birth voltmeter. However, due to the strong energy dependence of the response, its uncertainty is in the order of 30 to 50%. To accurately assess the neutron dose, the symmetric system should cover the entire neutron energy range and should provide accurate information on the neutron energy distribution. This can be done through neutron spectrometry. The Bohner sphere spectrometer is generally considered the standard for neutron measurements because of its isotropic or nearly isotropic response and its capability to cover a broad neutron energy range. Measurements around high-energy photon linacs can be made with uncertainties in the order of 3% influence and 7% in the dose. Neutron spectrometry is an active research field in the world, and this is the first time that the neutron fields in the Medical Linear Accelerator facility has been evaluated in the Philippines. This study aimed to evaluate the neutron fields generated by a 15 MV linear accelerator using a passive modified Bohner sphere spectrometer with indium foil as central detectors. The methodology has four main parts: irradiation, gamma spectroscopy, saturation activity calculation, and neutron spectrum unfolding. For the irradiation, we have a portable assembly type system consisting of concentric, high-density polyethylene spherical shells with an indium foil thermal neutron detector. Spectrometric measurements were carried out in one of the treatment rooms of the lung center of the Philippines around the 15 MV variant Linac CX linear accelerator. The following Linac parameters were employed during each irradiation. There are also three selected measurement points inside the treatment room. Location 1 is the isocenter, location 2 70 centimeters away from the isocenter, and location 3 is the maze room junction. After the irradiation of the Bohner spheres, gamma spectroscopy was then performed. The induced activity in the irradiated indium foil was measured using a portable integral-style sodium iodide scintillation detector coupled to a 14-pin PMT-based, DG-based compact module. The indium foil technique relies on the post-irradiation counting of the gamma rays emitted by indium-116M induced by neutrons on thin foils of indium-115. Here, the count rate indicates the quantity of thermal neutrons. The alivro plot is a graph of the saturation activity versus the sphere diameter. The saturation activity induced in each indium foil detector was calculated using this equation. Now we proceed to the results and discussion. Figure 1 shows the plots of the saturation activities for each sphere detector combination for each measurement location. Location 1 has the highest induced saturation activity since the isocenter is where the useful high-energy photon beams would directly pass through. The activity decreases as the measurement point moves away from the isocenter. Figure 2 shows the liturgy representation of the neutron spectra in the semilab plot to illustrate the relative distribution of the neutron components inside the Linac room. The measured neutron spectra displays two prominent peaks, one in the thermal neutron energy range and one in the fast neutron energy range. An extended intermediate neutron energy range is also present. The fast neutron component is dominant at and near the isocenter L1 and L2 and decreases with increasing distance from the X-ray target following the inverse square distance law. The thermal and intermediate neutron components of L1 and L2 would slightly vary since the treatment room surface area is invariant. Location 3, there is relatively small fraction of neutrons produced in the high energy range, since the majority of the neutrons are low energy neutrons due to the thermalization of the fast neutrons through multiple elastic scattering. The liturgy spectra that is normalized per 1 gray dose into the best estimate of the fluence for each measurement location is plotted in figure 3 to compare the absolute distribution of the neutrons. The spectra of locations 1 and 2 almost coincides with small deviations in the thermal and fast neutron energy range since these locations are close to each other. Location 3 is an order of magnitude lesser than that of other locations. This is further supported by the fluence distribution of each neutron component in the total neutron fluence shown in Table 2. The integral quantities calculated for each measurement location as provided by the fruit code are summarized in Table 3. A decrease in neutron fluence with increasing distance from the source is observed. For the ambient dose equivalent, the fast neutrons have the largest influence, while thermal neutrons had small effect on each star 10. The neutron dose equivalents in the treatment room were measured to be 2.24, 0.72, and 0.076 millisievert at locations 1, 2, and 3 respectively. Putting this into context, a lung cancer patient undergoing 60-gray radiotherapy treatment with 15 MV photons receives an additional total neutron dose of 134.4 millisievert at a target site positioned at the isocenter, while the non-target areas, which are the critical organs, would receive a total neutron dose of 43.2 millisievert. Table 4 shows a comparison of the neutron fluence and H*10 values obtained in this work with those reported in the literatures, which also carried out neutron spectrometry using a passive Bohner sphere spectrometer. It is noteworthy that the two quantities obtained near the isocenter of this study have a general good agreement with the reported literatures. From these results, we arrive at the following conclusions. The neutron spectra at three selected measurement points in the treatment room of a 15 MV variant cleanup CX linear accelerator were characterized using a modified passive Boner sphere spectrometer. Neutron fluence and ambient dose equivalents were obtained from these measurements. It was found out that neutron fluence is maximum at the isocenter, and the ambient dose equivalents were primarily influenced by the fast neutrons. The calculated values of the neutron fluence and H*10 values from this work agrees with the reported literatures. Thank you for listening.